last video you get to watch for the semester. Every problem on the final exam review that I'm about to do here is either from another test review or from a homework assignment. I don't think there's a single problem that's new, something that you haven't seen before. I also, at the end of this review, there's answers. I have the answers right next to me, so I can check myself as I'm working just to save some time, because I think this is going to take the better part of 2 hours without doing a lot of checking, and if I started throwing some checking into the mix, it's going to make it take 3 hours, and I don't know if you want to sit through that. So problem 1 wants me to find an equation of a line and write it in the y equals mx plus b form. So my answer for number 1 is going to be something, y equals something times x, and then plus or minus a number. And to the left of the x, there's going to be the slope. And after the x, there's going to be the non-zero part of the y-intercept, which may be plus or minus. So this sign could actually be minus. It won't be both a plus and a minus. It would be one and the other, or the other. I do know the slope, so I don't have to worry about trying to find it. So I have half of my answer for free. The only thing I need to stumble upon is the b. So I'm going to do all the algebra for this problem is just to solve for b. I'm going to use the equation y equals mx plus b. And into that equation, I'm going to plug m equal to 2/3, x equal to 6, and y equal to 5. And when I do that, I get 5 equals 2/3 times 6 plus b. When you multiply the 5 times the 2/3, or the 2/3 times the 6, the 6 cancels with the 3 and turns into a 2. Makes the fraction go away. It leaves me with 2 times 2, which is going to be 4. So I get 5 equals 4 plus b. And I'm going to minus 4 from both sides. And when I do that, I get 1 equals to b. That I need to put in my answer next to the 2/3 x. So I'm going to write my answer as y equals 2/3 x plus 1. My black marker is no way going to make it through this video. And I'm going to run back to my office and get a new one. Otherwise, it's going to look ugly. So there's going to be a big pause here. Sorry about that. This one hopefully is better. So that's all there is to do for problem 1. Problem 2 is one notch more difficult because it asks me for the same sort of answer. It wants an equation for a line, but I don't see the m, nor do I see the b. So my answer, or the form of my answer, is going to be y equals mx plus b. I need to replace the m and the b with numbers that fit the problem. And unlike the last problem, I wasn't given the m. So when I go to write my answer, it's going to be y equals, and there's going to be a number to the left of the x, which is the slope, and a number after the x, which is the y-intercept. In this case, it's a minus. So the first thing I'm going to do is find the slope. I'm going to use the slope formula. The m equals y2 minus y1 over x2 minus x1. So I'm using y2 of 5 minus y1 of 1 divided by x2, which is 4, minus x1, which is 3. If I do this math, I get 4 over 1, which is 4. So in my answer to the left of the x, I know the 4 is the number that I need. And now that I have the m, I can go about finding the b. I'm going to use m equal to 4. And I could use either point. I'll pick the first point. X equal to 3, y equal to 1, and the formula y equals mx plus b to help me find the b. So into that formula, in for y, I'm going to plug 1. In for m, I'm going to plug 4. In for x, I'm going to plug 3. I'm going to leave the b alone. I'll do the algebra. The algebra here is going to give me 1 equals 12 plus b. And then I'll minus 12 from both sides. And when you do that, you get negative 1, or negative 11, equals b. And I'll write that in negative 11 right after the 4x. I could have written plus a negative 11, but that certainly wasn't necessary to write a plus a negative, and a minus is just as good as a plus a negative. And that's as good as I'd expect for number 2. You do a lot of finding equations for lines in brief calculus and regular calculus, so that this is, it's a big deal in some sense. 3 and 4 want me to find x and y intercepts. For a fraction, to find the x-intercept, you set the numerator equal to 0. You could ignore the denominator. So I'm going to ignore the denominator. And I'm going to solve the numerator equal to 0. So for any fraction, this is a strategy that will work for finding the x-intercepts. When I do this, because there's a square, I'm going to solve by factoring. This factors into x plus 1 times x minus 6. Now that I have it factored and set equal to 0, I'll split the factors up, set each one separately equal to 0. For the x plus 1, I'll minus 1 from both sides and get x equal to negative 1. For the x minus 6, I'll add 6 to both sides and get x equal to 6. When I go to write my answer to this problem, for the x-intercepts, I'm going to write them as points. I'm going to say it's the point negative 1, 0, and 6, 0, because by setting the numerator equal to 0, I've kind of placed 0 in for y. The computation for the y-intercept is way easier. You just plug 0 in for the x's. So all you do is just let x equal to 0. I'm going to go y equals to 0 squared minus 5 times 0 minus 6 over 0 plus 1. All the pieces with 0 go away, and I'm just left with negative 6 over 1, which reduces to negative 6. So in my answer for the y-intercept, I'm going to say it's the point 0, negative 6. I put 0 first because I plugged in 0 for x and got negative 6 for y. That's why I write it as a point like that. And that's everything there is for 3. I don't know if 4 is harder or not. It's not that much harder. It's different though. It's not a fraction. To do the x and y intercepts for number 4, I'm just going to be plugging in zeros into the entire problem. So for the x-intercept for number 4, I'm going to let y be 0. And I'll go x squared plus 0 squared equals 121. The 0 squared goes away and I'm left with x squared equals 121. I can solve this by factoring if I took the time to set the problem equal to 0, or I can solve it by square root plus or minus square rooting, and that's more efficient. On the left side, square rooting cancels out the square, just leaves me with the x. On the right side, I happen to know the square root of 121 is 11. So in my answer to this problem, the x-intercepts, there's going to be 2 of them. I'm going to write each of them as points. I'm going to write 11, 0 and negative 11, 0. Turns out that the y-intercept computation really isn't going to be any different. For the y-intercept, I let x equal 0, but the algebra is going to turn out to be the same. The beginning step looks subtly different, but after the beginning step, it's going to start to look a lot alike. When I plug 0 in for the x, the 0 squared goes away, leaves me with y squared equals 121. And again, it's probably best to solve this by doing square root plus or minus square root. Square rooting cancels out the square on the left side. It leaves me with the y. On the right side, the square root of 121 is 11. So for the y-intercepts, I'm going to write 0, 11, and 0, negative 11 for my answers. Oh, right. There's a ton of problems on this. I mean, there's 30-some problems, but some of the problems have multiple parts. So there's probably really 50 or so problems. For the next 4 problems, they want me to find the domain and the range. 5 is like one of these things is not like another because it's a series of points. And in 5, the domain and range is going to be written in with set bracket notation. And I'm just going to list the proper coordinates. Specifically, when I go to write the range for number 5, I'm going to write the x-coordinate of all the points, which are 3, 4, 5, and 7. I can write them in any order, but if I look at the 4 points, each point has a different x because this is a function, and the x-coordinates are 3, 4, 5, and 7. When the points on a graph are disconnected, the domain and the range are just the individual x and y coordinates. The range is going to be the y coordinates. That point has a y coordinate of -1. Those 2 points have y coordinates of 2, which I don't have to write the 2 twice, but it wouldn't be wrong to write it twice. And that point has a y coordinate of 6. So that's all there is to do for number 5. The rest of these problems, 6, 7, and 8, the domain and the range is going to have interval notation. Problem 6 is a little bit different than 7 and 8 because the points at the ends are labeled and this graph doesn't need to be extended. To do the domain, I need to know the far left point, and that point right there is the point 0.5 is the far left point. And I need to know the far right point, and this point 50 is the far right point. The domain, I get the x-coordinate of the far left point first, and then the x-coordinate of the far right point. I get square brackets if there's points on the graph, which those are. So the domain is the x-coordinate of that far left point, which is 0, and then the x-coordinate of the far right point, which is 5. Square brackets because those points are actually on the graph. To do the range for number 6, I need the y-coordinate, and I have to identify the bottom point and the top point. And for number 6, the bottom point is the point 0, -5. Its y-coordinate is -5, so the first number in my range is going to be -5. The top point is the point 3, 4. Its y-coordinate is 4, so the end of my range is going to be 4. So it would be appropriate to write the range to be -5 and 4. The next 2 problems need to be extended. Problem 7 needs to be extended down and to the left, which means it extends all the way to the left edge of the x-axis, which is the -x direction, and to the bottom of the y-axis. If you go down far enough, then that's the -y direction. So this is the extension of the graph. So first, for number 7, you need to only extend the left side. The right side has a period at the end, which means it doesn't need to be extended. Fortunately, there's only 2 points labeled, so those points have to work for both the domain and the range. This point right here is the far left point. Its x-coordinate is -infinity. So in my domain, I'm going to say the first thing I'm going to write is -infinity. Because -infinity, this point's not actually a point on the graph, I get a round bracket. The far right point is the point 0, 2, and its x-coordinate is 0. It's actually a point on the graph, so I should get a square bracket there. When I do the range, I go bottom to top, and this far left point is also the bottom point, and its y-coordinate is -infinity. So I pick the bottom y for the range, And then the point 0, 2 is not only the right point, it's also the top point. And I pick off the 2, which is the y-coordinate of the top point. And that's all there is to do for that problem. 8 needs to be extended both directions, down and to the left, up and to the right. Up and to the right, it goes to the double positive infinity, and down and to the left, it goes to the negative infinity, because left is negative in the x direction, down is negative in the y direction, and similarly, up and right are the positive directions for x and y. Just like the last problem, there's only 2 points labeled. This point right here is the bottom point, and its x-coordinate is negative infinity. So when I go to write the domain answer, I'm going to start it off with a negative infinity, which is the x-coordinate of the bottom point. And then the top point's x-coordinate is infinity. Because neither one of those infinities are actual points on the graph, I should get round brackets. The bottom point, bottom and top was probably more appropriate for the range. It's left and right for the domain, so I messed up here. My answer is right, but for the wrong reason. This right here, I should have said range, because the range, you take the bottom y and the top y. So bottom y and the top y make the range. And then for the domain, I need the left and the far left and the right points, and I need their x's. The far left points has an x-coordinate of negative infinity, and this point, that's also the top point, is also the far right point, and its x-coordinate is infinity. Turns out that mistake would have been a forgiving mistake because the x's and the y's in each of the points are the same. You couldn't really pick the wrong one, but I did. The range is the bottom y to the top y. The domain is the left x to the right x. You do a decent amount of domain and range in brief calculus as well. I tried to pick problems on the review that if you're taking brief calculus or math 220 calculus that you're going to see. I didn't try to just randomly pick problems that I didn't think you were going to see in a higher class, although there's a few problems that might not be really emphasized in calculus. Most of what I put on this review is very specifically things that you're going to see in a higher class. So 9, 10, and 11 ask me to find the domain but not the range using algebra and write my domain in interval notation. There's 3 different styles of problem. Each problem has its own strategy for finding the domain. For 9, to find the domain of a fraction, you ignore the numerator. I'll write top. You solve the denominator equal to 0. And that doesn't give me the whole domain. It gives me the numbers to exclude from the domain. So when I do the algebra, x squared minus 6x minus 7 equals 0, I factor it and get x plus 7 times x minus 1 equal to 0. And then I take the factor x plus 7, set it equal to 0. The factor x minus 1, set it equal to 0. I get 2 answers, negative 7 and positive 1. And those numbers need to be excluded from the domain. To write my domain in interval notation, I can create a number line that has negative infinity at the far left end, positive infinity at the far right end, and the numbers that I want to exclude from the domain written in the proper order, smallest to biggest, between the infinities. And now I'm going to put round brackets to form the intervals that I'm going to need. So my answer to what the domain for number 9 is, it's going to be 3 disjoint intervals separated by union symbols. It's going to be the interval from negative infinity to negative 7, and then a union symbol, and then again the interval from negative 7 to 1, and then another union symbol, and then the interval from 1 to infinity. So 9, its algebra for finding the domain is completely different than 10, which is completely different than 11. To find the domain of a fraction, you ignore the numerator, you solve the denominator equal to 0. If you would have written your answer as the domain is all real numbers except -7 and 1, I'd give you credit. The instructions say to write the domain, the answer in interval notation, so I did it. But it would be okay to say the domain is all real numbers except -7 and 1. I just want to show you interval notation just in case you're taking another math class and your teacher likes the interval notation. Somehow it's more mathematically elegant than using the shorthand. For the domain of a square root, you just set the argument, drop the radical symbol. So the algebra for this is you drop the radical and you solve the argument. That's the thing that's under the radical is greater than or equal to 0 to find the domain. And unlike doing the domain of a fraction, this is an acceptable answer. If for this problem, all I did is take the x plus 5 under the radical, set it greater than or equal to 0, and wrote down x is greater than or equal to -5, that would be the correct domain. It's just not written in interval notation. And as an interval, that's any number -5 or larger, which is anything between -5 and infinity. So the answer that's asked of me is the interval from -5 to infinity. But if on the final exam you wrote this is an okay answer as well. If all you said is the domain is x is greater than or equal to -5, that's acceptable. Just similarly, like there's multiple ways to write the domain of a fraction, there's multiple ways to write the domain of a square root. 11, if you have 3 anywheres in your answer, that is the x-intercept for that graph, and that has nothing to do with the domain. 11's a polynomial. All polynomials, there's no algebra to do for the domain. The domain is just negative to positive infinity or all real numbers. So if you do any algebra, you're likely finding the x-intercept. And so I'm just going to write negative to positive infinity and be done. So the answer to what the domain of problem 11 is negative to positive infinity. And again, if you did any algebra, the algebra is very likely wrong. And it's very likely the algebra gave you the number 3, which was the x-intercept. Okay, that's 11 of the problems, but these were all the quick problems. The lengthy problems are starting to come up, and here's the first lengthy one. So the intervals where the function is increasing and decreasing are the first things that 12 asks for. And if I want to look at this graph, when it's doing this is increasing. So there's 2 regions where the graph is increasing as I move from left to right. Because as I move from left to right, the graph is getting higher. And in this little piece in the middle, this is where it's decreasing. So decreasing, as I'm drawing it, I'm going downhill from left to right. As I'm increasing, I'm going uphill from left to right. For each one of these problems, if I wanted to focus on this graph for increasing and decreasing, I might want to look at the graph just like this. So here, the far left point, this graph gets extended down. The far left point is negative infinity, comma, negative infinity, but I don't need the y coordinate. This point right here has an x coordinate of -3. And in that region right there, from x equals negative infinity to x equals -3, the graph is increasing. So I'm going to say the graph is increasing in the region from negative infinity to -3. Always round brackets on the increasing and decreasing, because at the point where it changes directions, it's not increasing nor decreasing. And then if I continue drawing the graph, this region right here to this point, -1 comma something, this is where the graph is decreasing, and it's the only interval the graph is decreasing. And I'm going to write that using the x coordinates. I'm going to say it's decreasing from -3 to -1. And then the last part of the graph, the rest of the graph all the way up from the point -1 comma 12 all the way to the point double infinity, the graph is increasing again. And I'd say this last region that it's increasing is from x equal -1 to x equal infinity. I'm going to put a union symbol between the two different intervals, and that would be the best we can do for an answer. This particular graph has a local maximum, this point -3, -8. It's a high point. We call it a local maximum. Some calculus books will call this a local maximum, some will call it a relative maximum. And the point -112, which is a little bottom point, it's a little low spot, we call a local minimum. So little humps are little high humps and low humps, we get maximums and minimums. C wants me to find the x value of where it has a local maximum. The x value where it has a local maximum is x equal to -3. The local maximum value is the y value of the maximum, and the y value of that maximum is -8. Part E says find any values of x where the function has a local minimum. That's at x equal to -1. And then it says for part F, find the local minimum values. The local minimum values is the y coordinate of the minimum. In this case, it's -12. So problem 12, there wasn't any algebra to do. You just have to understand what it means for a function to be increasing and decreasing. Increasing as I draw from left to right, the graph is going higher. Decreasing as I draw from left to right, the graph is going lower. And when I write down intervals for increasing and decreasing, they only include x coordinates, never include y coordinates, and they only ever have round brackets, never have square brackets. That's another big deal. You do a ton of increasing and decreasing in both brief and regular calculus. So this particular final exam review is loaded up with things that you're going to see again in calculus. There isn't a single word problem on this test. Not that there aren't word problems in calculus, but I just wanted to focus on the algebra skills that are going to make you successful in calculus on this review as much as anything. Average rate of change is also something you do at the beginning of calculus. The average rate of change, so the average rate of change is just the slope of the line. That connects 2 points on the graph. And what I've been given are 0 and 2, which are the x coordinates of 2 points. The 0 and 2 represent x coordinates of points on the graph. I need to find the y's. I need to find a y for each x. And I'll do that by plugging 0 and 2 to the function. So when I plug 0 into the function, I'm going to get 0 cubed plus 6 times 0 squared. This is going to give me 0 plus 0, which is 0. So that's going to tell me that the point 0, 0 is a point on the graph, and one of the points that I'm interested in. When I do f of 2, I get 2 cubed plus 6 times 2 squared, which is going to be 8 plus 24, because 6 times 2 squared, you do exponents first, so this is 6 times 4, which is 24, and that's going to be 32. So the other point that I'm interested in is the point 232. So the average, and I'm going to abbreviate average, rate of change is going to be the slope of the line that connects those 2 points. So I'm going to go y2 minus y1, 32 minus 0 over x2 minus x1, 2 minus 0. That's going to give me 32 over 2. And the answer to this problem 13, the average rate of change from 0 to 2 on this particular function is 16. Just checking my answers for the last few problems. I forgot to keep checking. No mistakes yet. Oh, right. 14 wants me to describe how a graph gets moved, and 14, 15, and 16 are all just basic transformations. For 14, this graph is going to be a parabola. It's going to have the same shape as, we'll say, f of x equals to x squared, but it's going to have two movements. The plus 2 inside the parentheses is going to move it left 2. I'm going to do a real abbreviated answer rather than saying it's shifted left 2. I'm just saying it's going to move left 2. So inside a parentheses, under a square root, or inside an absolute value, plus is left, minus is right. And then after the function, plus is up, minus is down. So in this particular function, the plus 2 inside the parentheses moves it left 2. The minus 4 after the square moves it down 4. 15 is going to have the same shape as the square root of x. There's three things going on. The negative in front of the parentheses flips it over the x-axis. There won't be any reflecting over the y-axis on the test, on the final. The minus under a radical is like a minus inside a parentheses, and it's going to move it right 3. And the minus afterwards is like the minus 4 up there, and it's going to move it down 5. So it's just a matter of knowing what each plus and minus does to the graph. 16, the graph is going to have the same shape as f of x equals the absolute value of x. That you really don't need to include in your answer, but it's okay to include it in your answer. The minus inside or under the absolute value is like having a minus inside a parentheses or a minus under a square root, and that's going to move it right 3. And the plus 4 is going to move it up 4. There's no reflecting because there's not a minus outside the absolute value like there was in 15. And there's no algebra to do for any of those problems, 14, 15, and 16. They're just kind of, you just remember how to move a graph left or right, up or down, and reflect over the x-axis are the only things you have to remember. There's no stretching or reflecting over the y-axis on the final. (17a), if I want to describe the how this graph compares to the graph of x squared, it's going to be right 3 for the minus in the parentheses, and for the plus afterwards, it's going to be up 4. So that's the part A. Part B says to make a table of values and sketch a graph. And when we did parabolas, we took the sign inside the parentheses, the number inside the parentheses changed its sign. Find that number on the x-axis, and then find numbers directly to the right of it and left of it. So I'm going to go 4, 5, 2, and 1. So that's the beginning of my table of values. It didn't say anything about not cheating, so I'm going to get my y's via my table on my calculator. So I'm going to go y equals, I'm going to go second whoops, I'm going to get to this plot, second stat plot, and turn my plot off. When I looked at this, that plot 1 was darkened out, and I knew that if I didn't get that plot taken off, it was going to mess me up. Now I'm going to clear out the function that's in there, type parentheses x minus 3 squared plus 4, do zoom standard. My graph is going to wind up looking just like that. And now when I hit second and table, hopefully, oh, it's so far. Oh, I have to make it all the way down to 5. And I don't know a fast way to do that. If I just type in 5, it didn't work. So I'm trying to find 5, 4, 3, 2, and 1. And for some reason, my calculator is at 100. I'm tired of doing that already. I'm going to hit second and table set. And table start, I'm going to start it at 5. And now hit enter. And do second table. It jumped it there for me. So now I can see the table I'm searching for. Next to the 1, I need the number 8. Next to the 2, I need the number 5. Next to 3, I need 4. 4, I need 5, and so forth. So next to the 1, I need an 8. Next to the 2, I need a 5. Next to the 3, I need a 4. Next to the 4, I need a 5. Next to the 5, I need an 8. You're completely welcome to steal any table like this from your calculator. It's not really that much of an algebra activity to get the y's if you needed to get them by hand, but you're not expected to do that. And I'm going to be very lazy and only plot 3 points because the 8s I don't think I'm going to be able to fit, and that's okay. 3 points, as long as one of them is the vertex, should be enough to give me a reasonable graph. So I'm just going to plot the 3 as opposed to the 5 points, but it's okay. I'm not going to get crazy on the test if you don't plot all the points that we might normally. And I'm not even labeling the points perfectly, but it's fine. So this would be part B, make a table and sketch a graph. To do the domain of this, I'll extend the graph up and to the left and up and to the right. It extends to the point negative infinity, positive infinity in the left direction, and positive infinity in the right direction. To do the domain, I want the far right and the far left points. I want their x-coordinates. The far left point is double negative infinity, positive infinity. Its x is negative infinity. So I'm going to write that first in the domain. And then I need the far right point, and its x-coordinate is infinity. So the domain is negative to positive infinity. Should have known that because it's a polynomial, and all polynomials have that for the domain. For the range, I need the bottom point and its y, which is net 4 on the graph, so it's going to get a square bracket. And then both of these points are equivalently at the top, and I can take either y, but they're both the same y. And the top of the range, or the end of the range, is going to be positive infinity, because range is bottom to top and y's domain is left to right. In terms of where this graph is increasing and decreasing for part D, this portion of the graph right here, this is the decreasing portion, and this portion of the graph right here, that is the increasing. And in terms of increasing and decreasing, so this region right here is decreasing, and this part right here is increasing, and I do the decreasing and increasing in terms of the x's. And don't include any y's in my answer to increasing and decreasing. So the interval here, from this negative infinity x to that 3x, as I'm moving from left to right, the graph is going downhill. So from negative infinity to positive 3, the graph is decreasing. At 3, it's not increasing or decreasing, so I get a round bracket there. And then again, from 3 to infinity, from x equal to 3 to x equal infinity, the graph, as I move from left to right, is going up, so it's increasing. For part E, the turning point's a minimum point, so it doesn't have a local maximum. So it has, we'll say none for part E, because it has no local maximum. Part F, the x value of the local maximum is 3, and the y value is 4. So we can say there's a local maximum, local minimum not maximum, occurs at x equal to 3, and the minimum value is y equal to 4. That would be the nicest way to answer that. Maybe a way that you'd be expected to answer that in a calculus class. So everything on here, every bit of this problem, you'll see again in a calculus class. One big thing that's going to be different is this 0.34 you're going to get using calculus without, like me, I kind of give you the table. I give you a strategy for finding the table ahead of time. But in calculus, you'll find a way to know what the table should be or know what this point should be using some calculus. So that's everything for problem 17 that you need to have. 18 looks like it's a messy problem. Use synthetic division to factor the polynomial. In order to use synthetic division, I have to find an integer place where the graph crosses the x-axis. So I'm going to find an x-intercept using my calculator. And there's only going to be one, I think, because when I look at the answers, it looks like there's only one. Or if there's two, the other one, there's only one integer one. So I'm going to graph the function x cubed plus x squared plus 2x plus 2. So just graph it. Look to find an x-intercept. It looks like there's an x-intercept at -1. I'm going to make sure there's an x-intercept at -1 by going second table, finding -1, and making sure there's a 0 next to it in the y column, which there is. So that means x equals -1 is a 0, or a solution to the initial problem, x cubed plus x squared plus 2x plus 2 equals to 0. It also means x plus 1 is a factor of x cubed plus x squared plus 2x plus 2. I'm going to first use synthetic division to factor the polynomial. So I'm going to take the solution, -1, or the 0, and pull off the coefficients of that polynomial, which are 1, 1, 2, and 2, and do my synthetic division. Bring the first number down, multiply, add, multiply, add. Really? Multiply, add, multiply, add. I'm stumbling right here, trying to figure out what my mistake is before I say something, because my remainder has to be 0, and I'm not getting 0 right now. 2 plus multiply, add. Really? X equals -1, x plus 1 is a factor. 1 squared, 2, 2. Bring it down, multiply, and I found my mistake. I did -1 times 0. I should have got 0. I knew I was making a mistake, just couldn't find it, and that was a trivial mistake. I did -1 times 0 and said it was -1. -1 times 0 should be 0. 2 plus 0 should be 2. Now I can fix this. I'm going to multiply -1 times 2 and get -2. Add and get 0. So this becomes x squared plus 0x plus 2. And specifically, what the synthetic division has given me the ability to do, so now I can know that the x cubed plus x squared plus 2x plus 2 equals to the factor that comes from the 0, x plus 1, times the remainder, x squared plus 2. So now I know how to factor this. So now I can solve this. So it says use synthetic division to factor the polynomial. That's what I did. Now I can solve. So now I can figure out the answer to the problem. So I'm going to solve, very specifically, the equation x cubed plus x squared plus 2x plus 2 equal to 0. First step, factor. This factors into x plus 1 times x squared plus 2 equals to 0. It's factored as far as it factors. This is a sum of squares. It doesn't factor more. It's set equal to 0 in factors, so I'm going to split each factor up and set each one separately equal to 0. For the x squared plus x plus 1, I minus 1 from both sides and get x equal to negative 1. For the x squared plus 2, I first minus 2 from both sides and get x squared equals negative 2. And then I square root plus or minus square root. The square root of x squared is just x. The square root of negative 2 doesn't really reduce, but you do get an I because you're taking the square root of a negative. So the answers to the problem solve the equation x cubed plus x squared plus 2x plus 2 equal to 0. The answers that I had to do all this work to get are x equal to negative 1 and plus or minus I square root of 2. I don't know of another way to get that without synthetic division. At some point, this needs to be solved by factoring, and I didn't know how to factor that. Actually, grouping might have worked. You could have actually probably factored this by grouping if you remembered grouping from some other class. You could have actually got it that way. It was a special problem that grouping it doesn't always work, but grouping would have actually worked here. So if you were super clever and you did this by grouping, I'd absolutely give you credit, because even though it doesn't say to use grouping, if you did that, that's being ultra clever, because we haven't done grouping this semester. All right, 19. So these are fraction problems. Wants me to do the stuff with the graph and label the features of the graph. The first thing I'm going to do is part A is find the domain. And I'm going to write the domain in words because that's how I have it written. To find the domain of any fraction, you ignore the numerator, you set the denominator equal to 0. That's the number you exclude from the domain. So the domain here is going to be all real numbers except 3. If you said the domain was 3, that would not be good, because that's the only number that you can't plug in for x. Well, you can plug it in, but if you plug it in, you get undefined. But the vertical asymptote, the vertical line where the graph is going to exist on either side of, is that equation. So the answer to part B is going to be x equal to 3. And now I'm going to start doing my graph, and I'll just throw it up here. Eventually I'm going to borrow the graph from my calculator. The first thing that's going to happen that I'm going to draw on the graph is a dashed vertical line through 3. And that's the vertical asymptote. The graph is going to exist on either side of that, but it won't cross that. For the horizontal asymptote, I write y equals, I take the highest power of x in the numerator, which is the 2x term, the highest power x term in the denominator, which is the x. I reduce that fraction by canceling out the x's, and I get y equal to 2 for the equation of the horizontal asymptote. And that's the next thing I'm going to draw. I'm going to find 2 on my y-axis, and I'm going to draw a horizontal line through it. I don't think this graph is going to cross that horizontal asymptote, but they can. For the x-intercept part in numbered part D, you just take the numerator and set it equal to 0. So I'll take 2x plus 6 and set it equal to 0. I'll minus 6 from both sides and get 2x equal to negative 6. I'll divide both sides by 2 and get x equal to negative 3. So the x-intercept is going to be the point negative 3, 0. And again, I'll label that on my graph the best I can. This is probably not the best representation. It's not drawn to scale, but it's good enough. Last thing I need to do by hand is the y-intercept. For the y-intercept, you're plugging in 0 for x, so I'll go 2 times 0 plus 6 over 0 minus 3. That's going to be 6 over minus 3, which is minus 2. The y-intercept is going to be the point 0, negative 2. And again, I'll kind of plot that as well. The rest what I'm going to do for part F is I'm going to sketch a graph. I've labeled all the features. There's the vertical asymptote, horizontal asymptote, x and y intercepts, and the domain that kind of shows up on the graph. So now I'm just going to do a standard window and see what happens. On the test for this, you'll be given a blank graph just like you were on the fraction test during the semester, so you won't have to worry about figuring out what the window is. I might have to worry about figuring out the window right now because the standard window might not work so well, but I think it works just fine. That standard window, it gives me a reasonable graph. I can't see either the vertical or the horizontal asymptote. If I want to see them, to do the horizontal asymptote, I could just type y2 and write equal to 2. Now you can see the effect of the horizontal asymptote. It might be better if I made my graph go further to the right, but I'm going to live with that. And I can't really graph the vertical asymptote perfectly, but I can cheat. If I want to do the vertical asymptote, I can do like 1,000 times the like x times really the denominator here, x minus 3. And if I hit graph there, it'll make it something look like the vertical asymptote. So that's what I'm going to do. I'm just going to copy that picture onto my graph that I've started. Make sure to go through the intercepts. If I stretch the window out farther, you'd see the effects of the asymptotes. Like if I made the window go to the 20s as opposed to the 10s that it is doing, then you'd start to see the asymptotes take over. But I don't really see the asymptotes take over in the standard window as much. So if on a test I might have actually set the window up like that, and you might get get to draw that as opposed to the Zoom standard that produces that. They're both correct graphs. There isn't anything that's more correct about having the window at the 20s than it is at the 10s. It's just that maybe at the 20s you could see the impact of the asymptotes a little bit better. But you won't have to worry about figuring out a window. The window will be given to you because you'll be given a blank graph with the window on it. All right, the next problem, I'll have to tweak the window a little bit. It's not such a clean one like this, where a standard window was going to work just fine. So 19 wants me to do the same procedure. First, find the domain and the vertical asymptote. Those go hand in hand. So to do the domain, I take the denominator, ignore the numerator, and set it equal to 0. I set this up to factor. Once I get it factored, I split the factors up and set each one separately equal to 0. And that gives me the numbers to exclude from the domain. It also gives me the equations of the vertical asymptote. So for this problem, for part A, the domain is all real numbers except -7 and 3. For part B, the vertical asymptote, which I'll write as VA, is x equal -7 and x equal to 3. So when I go to do my graph, I'm going to draw a dashed vertical line through -7 and +3 on the x-axis. And again, I don't need to be horribly accurate here. So when I go to do this, I'm going to find something that I'll call -7 on the x-axis. Since I don't have a blank graph in front of me that's marked out, I'm doing a really crude graph, but this is good enough. So there's my vertical asymptotes. Now I do my horizontal asymptote. There's no slant asymptotes on the test. So horizontal asymptote, I do y equals the highest power of x in the numerator is x. The highest powered x term in the denominator is x squared. This really is x over 2 x's. So one of the x's cancel, and I can't write a fraction without a numerator. That leaves me y equals 1 over x. When you're left with an x in the denominator, the equation of the horizontal asymptote is y equal to 0. And that is the equation of the x-axis. So the horizontal asymptote for this particular problem is going to be the x-axis. And that happens because there's an x in the denominator when you do the division. part D to get the x-intercept. I take the numerator and set it equal to 0. E is no factoring there. That just gives me x equal to 1. The x-intercept is going to be the point 1, 0. And I'll just label that a little bit. So my graph is going to cross that horizontal asymptote there at 1, 0. And then the y-intercept is a really small one. I'm plugging in 0 for the x's. So I'm going to go 0 minus 1 over 0 squared plus 4 times 0 minus 21. And the pieces with the zeros are going to go away. So I'm going to get minus 1 over minus 21, which is 1 over 21. And the y-intercept on the right is 0 comma 1 over 21. And that's just going to be I'm just going to make a dot for it there. I'm not going to write the point because I kind of don't, my marker's too thick to show that. And now I need to get a window, and I don't know if you can read this, but it looks to me like if I go on the 20s on the x's and on the 10s on the y's, I'll get a reasonable picture. So again, you'd be given a blank graph to help you discover the window that's appropriate. So if I want to just do the graph itself, do x minus 1 divided by parentheses x squared plus 4x minus 21. And I'm going to change the window so that the x's are going on the 20s, but the y's are going on the 10s. I think that's the window that my key has. When I hit graph, it gives me a, maybe not that reasonable of a picture. I may crunch the y's down a little bit, maybe. Maybe make the y's at the 5s. I don't know if that works fine. Yeah, maybe. And maybe even make the y's at the 3s. Sorry. The key that I wrote, I used the computer program to graph, and the computer program makes better graphs than my calculator. So that's a reasonable graph. I could copy that into my screen right now. If I want to show the horizontal asymptote, I won't need to do that because that is the x-axis that's already shown. If I want to show the vertical asymptote, I can go 1,000 times x plus 7 and 1,000 times x minus 3. So to do this, if I do 1,000 times x plus 7, which was one of the factors of the denominator, that will give me something that looks like the vertical asymptote at negative 7. And if I do 1,000 times x minus 3, that will give me something that looks like the vertical asymptote at 3. So now I'll draw the asymptotes in. I'm just going to copy this picture. So it looks something like the graph in the middle does this. The upper right corner does this. The lower left corner does that. And you don't need to be any more accurate than that. You go through both the x and the y-intercept and have your graph, show how the asymptotes, how it approaches the asymptotes. That's more than adequate enough for problem 20. There isn't anything else other than that I'd expect you to do. So this would be an adequate graph. It shows everything that it needs to show. It shows the two vertical asymptotes, the horizontal asymptote, the x and the y-intercepts, and it does a reasonable picture at that. (21) and 22 you could solve using logarithms. So if you don't remember how to do the write both sides with the same bases, and you do them with logarithms on the test, that's okay. When you get into calculus, you're going to wind up solving problems like this and not be given any hint. So if you know how to solve the problem using a different strategy than I show you here, that's okay. 21 is easy to do writing both sides with the same base because it's easy to rewrite 27. If you make a prime factor tree for 27, 27 is 3 times 3 times 3, which is 3 cubed. So I can write this problem as 3 to the x minus 3 equals 3 cubed. 3 cubed. And if you could do that, if you could write both sides with the same base, you can solve the problem by dropping the bases and equating the exponents. And for this particular problem, that would give me an answer of x equal to 6, because when I add 3 to both sides, you get x equal to 6. 22, I'm just going to do it using logarithms. You could definitely do it without logarithms, but it's probably trickier than you'd care to, and I wouldn't expect you in a calculus class to pull out something that's subtle, pull out something that's relatively easy. And solving this with logarithms, although it's not the hint, it really is the way that would be best to attack this problem. So if you have an x that's written in an exponent, logarithms are generally a good way to solve the problem. So I took the logarithms of both sides. Now I'm going to make the exponent into a coefficient, put it in a parentheses. I'm going to get x minus 2 times the log of 1/2 equals the log of 1/8. Now I'm going to divide both sides by the log of 1/2. And this whole side I do on my calculator. The nice thing about logarithms is your calculator spits them up real easy. The left-hand side, I'm going to be left with the x minus 2. It won't need to be in a parentheses anymore. And then on the right-hand side, I'm going to enter basically what I see there, which is the log of 1 divided by 8 divided by the log of 1 divided by 2. So I'm basically entering exactly the left-hand side. Not that you can probably see it, but something like that. When I hit enter, it tells me, or the right-hand side, it tells me that the right-hand side should come out to be 3. So I can replace this with 3. Makes it super easy to get the answer now. If I would have tried to solve problem 22 like I did 21, I'd had to do a couple of kind of fancy things with the 1/8 that, yeah, maybe we don't want to get into this late in the semester. So the answer to problem 22 is just x equal to 5. And again, I'm checking all my answers because I have an answer key in front of me. There's certainly ways to check it outside without using the answer key, but again, I'm trying to save just a bit of time. 23 and 24 are kind of the same problem. They both problems that are structurally the same. They both have an x stuck inside a logarithm, and I'm going to solve them the same way by getting rid of the logarithm. So I'm going to scratch out the logarithm. I'm going to leave the 2 low, and I'm going to switch the 5 and the x plus 1 when I go to do problem 23. When I get to 24, I'll do something that's similar. I'll scratch out the logarithm, leave the 4 low. When I do this, 2 to the 5th, I don't need my calculator for. It's 32. I get 32 equals x plus 1. And then I'm going to minus 1 from both sides. And get 31 equals to x. Similarly, for 24, I'm going to scratch out the logarithm. I'm going to leave the 4 low. I'm going to switch the 3 and the x minus 5. When I do this, I get 4 cubed is 64 equals x minus 5. I add 5 to both sides and get 69 equals to x. So the answer to 23 was x equal to 31. The answer to 24 is x equal to 69, neither of which I had to check. There's one style of problem in the logarithm section that you do have to check, and that's coming up here in a second, but not the next one. 25, I'm going to use the rule that allows me to make 2 logarithms into 1 when they're separated by a minus. I'm going to start off using the minus to divide rule to rewrite the 2 logarithms on the left side as 1 logarithm. Now I'm going to do what I did in the last 2 problems. I'm going to write the problem without the logarithm. I'm going to leave the 2 low, and I'm going to switch the 1 and the fraction. I'm going to rewrite this so I can cross multiply. 2 to the first power is just 2. And any integer can be written as a fraction if you write it over 1. Now I'm going to cross multiply down and cross multiply up. When I do that, I get 2 times x plus 6 equals 1 times x plus 14. This gives me 2x plus 12 equals x plus 14. I'm going to minus x and minus 12 from both sides. When I minus x from the left side, 2x minus 1x is x. The 12's cancel on the left side. The x's cancel on the right side, and 14 minus 12 is 2. That's the answer. This wasn't the kind of problem that produced extraneous solutions, so in that one we'll check. The next problem, I can do perfect algebra, and I'll get two solutions. One will check and one won't check. And the big key, the red flag, is the plus between the two logarithms. So in problem 26, I'm going to write the two logarithms as one using the plus to times rule. So there's a rule that we learned that says two logarithms, same base, separated by a plus sign. You can make those two logarithms into one if you multiply the arguments. Now I'm going to do the multiplying by doing the FOILing. First are x squared, outers, inners, lasts. I'm going to combine the outers and the inners. And now I'm going to do what I did for the last few problems. I'm going to write it without the logarithm. I'm going to swap the 5 and the x squared plus 8x plus 12. 2 to the 5th is 32. Because there's a square, I need to set it equal to 0 and solve by factoring. So I'm going to minus 32 from both sides. And I get 0 equals to x squared plus 8x minus 20. I'm going to factor that into x plus 10 times x minus 2. I'm going to set the x plus 10 equal to 0 and get x equal to negative 10. I'm going to set the x minus 2 equal to 0 and get x equal to 2. And then I'm going to check in my original problem, so this is the checking part, that this is the only problem I think on the whole review that needs to be checked, because this is the only problem that has the potential of an extraneous solution. So I'm going to go to log base 2 of negative 10 plus 2 plus the log base 2 of negative 10 plus 6 and see if that equals to 5. I went to the original problem and I put in what I thought was the answer. And for this logarithm, I'll do just that. I'll do one logarithm at a time, and I'm going to get an error immediately. For this logarithm, I'm going to go the logarithm of negative 10 plus 2 divided by the logarithm of 2. And it's going to give me a non-real number, some sort of error message. So this one I get an error. It actually gives me an I when I do this. So this one doesn't check. Here I get an error. So negative 10 is not a solution. To check the 2, I'm going to go the log base 2 of 2 plus 2 plus the log base 2 of 2 plus 6. See if that equals to 5. And then on my calculator, I'm going to do the log base 2 of 4 plus the log base 2 of 8 and see if that equals to 5. I'll do each of these on my calculator. The first logarithm, I do log of 4 divided by log of 2. When I do that, I get 2. The second logarithm, I do log of 8 divided by log of 2. When I do that, I get 3. So that gives me 2 plus 3 equals 5, which gives me 5 equal to 5. Because that's a true statement, x equals 2 is the solution. And when I go to write my answer, I'm not even going to make a comment about the x equal to negative 10. I'm only going to write the x equal to 2. If you included the negative 10 on your answer, you'd have to say something about it not checking. So if you said x equals 2 and then x equals negative 10 is extraneous, that would be okay. But if you included the x equals negative 10 next to the 2 and didn't make a comment about it saying it doesn't check, or it's extraneous, meaning it doesn't check, then you're going to get dinged a point or two because you'd be including a solution that's really not a solution. Okay, almost to the newest stuff now. Solving by substitution. First problem, fractions there I don't like, so I'm going to take that top problem and get rid of the fractions. So I'm going to go 5 times 4/5 x plus, oops, I'm going to go 20 times 4/5 x plus 20 times 1/4 y equals 20 times 5. To clean up that top equation is tough to work with the way it sits. The 20 and the 5 will cancel. 20 divided by 5 is 4, leaving with 4 times 4x, which is 16x. This 20 and this 4 will cancel. The 20 will turn into a 5. I'm left with 5 times 1y, which is 5y. And to the right of the equal sign, 20 times 5 is 100. So I'm going to use that equation for a replacement for the top equation. And I'm going to keep the bottom equation, x equals y plus 1. And now I'm going to substitute. I'm asked to solve by substituting, so I'm going to go to the top equation and replace the x with y plus 1. So I'm going to go 16 times y plus 1 plus 5y equals 100. So the substituting I did is I took this x, put it in that y plus 1. Do the math here. This gives me 16y plus 16 plus 5y equals to 100. This gives me 21y plus 16 equals to 100. I'm going to minus 16 from both sides. When I do that, I get 21y equals to 84. Divide both sides by 21. I get y equal to 4. I need to solve for x. I'm going to use the equation x equal y plus 1 and go x equal 4 plus 1. That will give me x equal to 5. So my answer to this is going to be 5, 4. I could have done RREFA real quickly to check my answer before I started the problem, but I have my answer key in front of me, so I'm saving that step. 28 wants me to solve by the elimination method. I'm going to drop out the y's. I'm going to multiply the top by a 4, the bottom by a 3. That's going to force my y's to cancel. I'll make a positive and a negative 12y. So doing this, the top equation is going to become 8x plus 12y equals to 52. Multiplying the bottom by 3, I get 15x minus 12y equals 63. When I add these together, I get 23x equals to 115. I'm going to divide both sides by 23. And that's going to give me x equal to 5. Now I need to solve for y. And I'm going to use the top equation because the y is plus in it. So I'm going to use the equation 2x plus 3y equals to 13. Could have used any of the equations, but I like that because of the plus in front of the y. I change the x to 5. This gives me 10 plus 3y equals 13. I'm going to minus 10 from both sides and get 3y equal to 3. And then divide both sides by 3 and get y equal to 1. So my answer to this is going to be 5, 1. 5, 1. Next problem is the messy kind. Make sure I didn't drift off the screen. Got close, but I didn't. Next one's probably going to take 2 pages. Solves by hand without matrices. So system with x, y's, and z's gives me the hint to pair the middle with the other 2 and drop the x's. So I'm going to take the middle equation, negative x plus y plus 2z equal to 7. Write it with the top equation, 2x plus 4y minus 5z equals to negative 5. I'll take that same middle equation, negative x plus y plus 2z equals to 7. Pair it with the bottom equation, x minus 3y plus 3z equals to 4. To drop the x's from the first one, I'm going to multiply the top by 2. When I do that, it'll give me negative 2x plus 2y plus 4z equals to 14. I'll stack that on top of 2x plus 4y minus 5z equals negative 5. When I add these together, the x's cancel. I have 6y minus z equals to 9, assuming I haven't made a mistake. The next pair I could just add together and the x's will cancel out. X's cancel. Y plus negative 3y is negative 2y. 2z plus 3z is plus 5z. And 7 plus 4 is 11. Now I'm going to stack those two equations on top of each other. So I'm going to take the 6y minus z equals to 9, stack it on top of negative 2y plus 5z equals 11. I'm going to solve this by elimination. I'm going to multiply the bottom by 3 to drop out the y's. When I do this, I get 6y minus z equals to 9 on top of negative 6y plus 15z equals to 33. Adding this together, the 6y's cancel. I get 14z equals to 42. I divide both sides by 14, and I get z equal to 3. Now I need to solve for y, and I'll put it over here. To solve for y, I'm going to use the equation 6y minus z equals to 9, and plug 3 in for the z. So I'm going to go 6y minus 3 equal to 9. I'm going to add 3 to both sides and get 6y equals to 12. Then divide by 2 and get y equal to 2. Lastly, I have to find x. I'm going to use the equation x minus 3y plus 3z equals to 4. And into that equation, I'm going to plug in 2 for y and 3 for z. So that gives me x minus 3 times 2, which is x minus 6, plus 3 times 3, which is plus 9, equals to 4. Combining the minus 6 and the plus 9 gives me x plus 3 equals to 4. I'll subtract 3 from both sides and get x equal to 1. So my answer to this is x equals 1, y equal 2, z equal to 3. Could definitely do RREFA to check yourself, but it says to do it by hand without matrices, so I expect you to do that on the final if that's what's asked for. 30 and 31F fraction answers. I'm going to solve each of these by substitution. First one, I'm going to solve the top for x and then substitute in the bottom. So the top equation, x minus 7y equal negative 4. If I add 7y to both sides, I get x equals 7y minus 4. And now I'm going to substitute. So I'm going to take the equation, so sub now. I'll take the equation x squared plus y squared equal to 10. I'm going to change the x to 7y minus 4. So I'm going to go 7y minus 4 squared plus y squared equals to 10. I'm going to FOIL the 7y minus 4 because 7y minus 4 squared means 7y minus 4 times itself. When I do this, the firsts are 49y squared. The outers are a minus 28y. The inners are a minus 28y. The last are a plus 16. And now I'm going to combine like terms. I'm going to do the 49y squared plus 1y squared, which is this term. I'm going to combine those together. And for the numbers, I'm going to minus 10 from both sides. When I do that, 49y squared and 1y squared is 50y squared. Minus 28y and minus 28y is minus 56y. 16 minus 10 is plus 6. So I have the problem set equal to 0. There's a common factor of 2 that I could divide away. Which is going to give me 25y squared minus 28y plus 3 equals to 0. At this point, if you could factor it, it's better to factor. If you can't factor it, you could use a quadratic formula. I can factor. This is not too hard to factor. It factors into 25y minus 3 times y minus 1. You can use bottoms up to get there if you can't factor in your head. Or you could use a quadratic formula that would give you the same y values. Now that I have it set equal to 0 and factored, I split each factor up. The factor of 25y minus 3, I'm going to add 3 and get 25y equal to 3. And then divide by 25, I get y equal to 3 over 25. The factor of y minus 1, I add 1 and get y equal to 1. For each y, I need to get an x. So I'm going to use the two y's that I have. So this is problem 30. So the two y's that I have are y equal to 3 over 25 and y equal to 1. And the first thing I did is got x equal to 7y minus 4. So for the 3 over 25, I'm going to get x equals 7 times 3 over 25 minus 4. And I'm going to cheat, or be lazy, and go calculator on. X equals 7 times 3 divided by 25 minus 4. Decimal, then math, enter, enter. So x is negative 79 over 25. And then for the y equal to 1, I'm going to get x equals 7 times 1 minus 4, which is 7 minus 4, which is 3. So now I can write my answers to problem 30. My answers come in pairs. Each x and y are paired with each other. You write the x first and the y second. So one answer is the point negative 79 over 25, comma 3 over 25. The other is the point 3, comma 1. 31 is just about the same problem. In terms of it's ugly, you get a fraction answer again. I want to have a little bit of grunge on this review because there's a lot of bit of grunge in calculus. I'm going to do essentially the same thing for 31 that I did for 30. I'm going to solve the top for y, for x should I say. The top equation was x plus 2y equals 11. I'm going to minus 2y from both sides. I'm going to write x equals 11 minus 2y as opposed to minus 2y plus 11. And now I'm going to substitute. The bottom equation says x squared plus y equals to 13. I'm going to make this 11 minus 2y squared plus y equals to 13. And then the 11 minus 2y squared you have to FOIL. So I'm going to write it out so I can see the foiling easier. I'll do the firsts and get 121. Both the outers and the inners are minus 22y. The last are plus 4y squared. Still have the plus y and I have the 13. I need to combine all these three terms together. The 4y squared I can just write first, no problem. The minus 22 and minus 22 is minus 44, plus 1 gives me a minus 43y. And then if I minus 13 from both sides, 121 minus 13 is 108, positive 108. Ooh, that I can't do without a quadratic formula. So I'm going to use the quadratic formula. So I'm going to go y equals negative b, which is negative 43, plus or minus the square root of negative 43 squared minus 4 times 108 all over 2 times 4. I'm going to do the underside of the radical and get it down to a single number. The double negative in front of the 43 goes positive. The 2 times 4 is 8. And I'm going to get a number there. It's going to be a number without a square root. So I'm going to enter that just how it looks. I'm going to go second square root and then parentheses negative 43 squared, parentheses squared, minus 4 parentheses 108, 4 parentheses, really, parentheses 108, close my parentheses, close my parentheses. So real specifically, I have this on my calculator. I have square root and then bunch of parentheses, and then I have negative 43 squared in a parentheses, and then I think I have an extra 4 here. It should be minus 4 times 108. I have an extra times 4. So delete, delete, delete. That looks better. When I hit enter, it tells me that equals 11. And again, I probably couldn't do that in my head any quicker. So this is going to give me y equals 43 plus or minus 11 over 8. I'm going to make the two problems up. 43 plus 11 over 8, and y equals 43 minus 11 over 8. 43 plus 11 is 54. 54 over 8 reduces by 2 to 27 over 4. 43 minus 11 is 32, and 32 over 8 is 4. So I have two answers for y, specifically 27 over 4 and positive 4. Now for each y, I need to get a corresponding x. So I'm going to use the formula that I have and the y's that I have. So I have, this is problem 31, y equal to 27 over 4, as well as y equal to 4. I have the equation x equals 11 minus 2y that I came up with on the first step of this. So I'm going to get my x's. First x is going to be x equals 11 minus 2 times 27 over 4. Speed through this with my calculator. I'm going to go 11 minus 2 parentheses 27 divided by 4. Math, enter, enter, and I get negative 5 halves. So this gives me x equal negative 5 halves. For the other one, I'm going to get x equals 11 minus 2 times 4, which is x equals 11 minus 8, which is x equal to 3. So again, I need to pair each x with the appropriate y. One of the x, y combination is negative 5 halves, 27 over 4, and the other one is x equals 3, y equal to 4. I should write my x's first and my y's second. One more problem, of which I threw in right at the very end. As I was walking over here, I was like, oh, I better put this on the review because I know you see it in calculus all the time. Difference quotients you're going to see loaded up for the first 2 or 3 weeks of brief calculus and regular calculus. So to do this, I need to find f of x plus h minus f of x over h. First thing I need to do is find something to replace f of x plus h with. So f of x plus h can be replaced with x plus h squared plus 3 times x plus h minus 5, because that's what f of x plus h is. It's what you get when you plug in x plus h for the x's. I'm going to simplify this. So I'm going to get f of x plus h equals to, and I'm going to FOIL this. Firsts are x squared, outers are x times h, inners are x times h, lasts are h squared, and then the 3 times x is 3x, 3 times h is 3h, and minus 5 is minus 5. These xh's are both 1xh's, and they combine to 2xh. So I'm going to say f of x plus h equals to x squared plus 2xh plus h squared plus 3x plus 3h minus 5. I'm going to put that in the left-hand side of the numerator. I'm going to go to a new sheet of paper because what I'm about to write is kind of lengthy, but I'm going to take this with me when I take it to that new sheet of paper. So to find the difference quotient, to find f of x plus h minus f of x over h, I'm going to do this. I'm going to form a fraction. For f of x plus h, I have it written off to the screen here. I just found this, x squared plus 2xh plus h squared plus 3x plus 3h minus 5. The initial problem tells me what f of x is. I'm going to put f of x inside a parentheses, and f of x is equal to x squared plus 3x minus 5. And in the denominator, I don't need to know what h is, it's just h. So I took what was given to me, f of x, replace it with that, and what I computed, f of x plus h, and loaded up my numerator. Now I'm going to drop the parentheses and change some signs. So I'm going to get x squared plus 2xh plus h squared plus 3x plus 3h minus 5, and then minus x squared minus 3x and plus 5 when I distribute this minus through my parentheses. Lots of things will cancel. This x squared and that x squared will cancel. This 3x and that minus 3x will cancel. The minus and the positive 5 will also cancel. And that will leave me with 2xh plus h squared plus 3h over h. I'm going to factor out an h from the numerator. Be left with 2x plus h plus 3 all over h. And I'm going to cancel the h's. I'll be left with my answer. My answer to what the difference quotient is 2x plus h plus 3. If you took calculus in high school or took it before, this has something to do with the derivative. When you take the limit as h goes to 0, meaning when you plug 0 in for h, you get 2x plus 3, which is somehow the first derivative of the function that we're looking at. So that's the entire review. You'll notice there wasn't any word problems. I didn't want to force you to relive word problems so much. I just wanted to make your algebra skills as sharp as they can be for calculus. You should definitely, if you need to take brief calculus, take it as close to taking this course as possible, because your ability to succeed in calculus is all going to be hinged on your ability to do algebra, because the calculus itself isn't crazy hard. It's the algebra in a calculus class that will slow you down.